It's my honor to introduce Dr. Noel Keenlyside, and he is the professor of University of Bergen in Norway, and he's majoring in the climate dynamics modeling and prediction, and right now he leads the Bjerknes Climate Prediction Unit to develop the Norway climate model, and also extend to the very first one, the Earth system and the ecosystem models to proceed the climate services. And he also integrate several very large international cross-sector Europe and the Norway project. And he also involved in the WMO, WCRP climate project, including the Atlantic Regional Panel and the Climate Dynamics Panel, and also right now focus on the research of tropical basin interaction research. And let's welcome Dr. Noel Keenlyside to give us his keynote speech on European perspective on climate prediction and the services.
Thank you very much for the nice introduction. And I would say for the warm welcome, but actually I feel more like I'm in Bergen. With the temperatures in this room, it's quite cold. So I enjoyed the presentation this morning, but I will discuss it. I'll present material in a slightly different way and on different perspective. The first thing I want to say is that I can't remember the name of it. I think it's a physicist who said, you know, we can't predict the future. We can invent the future. Well, we can invent the future. That's what we should always be trying to do. And I'm going to argue that to some extent we can predict the future, at least parts of the future. Maybe not from a societal perspective. That's a bit more complicated. And the other thing, my presentation is going to focus on, with that, not on these longer time scales, but actually on the shorter time scales, and so not so much on mitigation activities, but more on a potential that climate information can be used for short-term adaptation. And so I'm going to actually give you a presentation about a European perspective. So this is essentially a talk based on a workshop we had in May in Bergen on climate prediction and services over the Atlantic Arctic sector. So the idea of the workshop was, you know, decadal prediction was started around in late 2010 or around 2007-8. And so where are we now, you know, almost 20 years later with this activity? And so this presentation, there's a lot of co-authors, you could say. So they're in this picture here. So it's difficult to probably represent all of the views at such a meeting. And so fortunately for me that I don't think there are any participants from the meeting in the audience, so I will not be corrected directly. But I would like to acknowledge these 4 people here. So these are helping in preparing the workshop paper that is coming out of this, and we are synthesizing material from the whole of the workshop in different groups, and these people are leading that activities. And so with that, let's get started. So I'd like to start off with just a definition of climate services. So there's lots of ways. I think it's not a very well-defined term yet. And so this is how we started off by defining it here. So climate services implies the provision of actionable climate-related information for use in decision-making in private and public sectors, either as one-off or as an ongoing service. We focus on climate services that both in some prediction information on sub-seasonal to decadal timescale. So this workshop focused on that period, that timescale. So not on end of century climate services. And we targeted the North Atlantic, Arctic or European sector. So in that respect, I've tried to make the presentation interesting for this audience, but a lot of the information here would not be directly relevant for you guys here. So just start off with a little bit of background. And probably many of you have seen this type of figure, but this is always our starting point when it comes to discuss climate prediction. We have on the left side here weather predictions. So this is sort of, we're at the Central Weather Administration, so you're very familiar with this. It's, the initial value problem. So the predictability comes from the initial state of the atmosphere largely. And on the right side here, we have the long-term climate change, so which is what Professor McCall had talked about. And this is the predictability here comes essentially from greenhouse gases, right, and other external factors. So how we're changing the external forcing on the climate system. But there's a range of timescales here from months to decades where both are important, where the initial condition of the, now not just the atmosphere, but the atmosphere, ocean, climate state are important, and where the long-term climate change, the effects of long-term climate change due to external factors is also important. So when we think about this shorter timescale, and I've just mentioned that the state of the climate system is important for the predictions. It's sketched here what are the most important in terms of the initial value. So for the shorter timescales between what we refer to as subseasonal, the land surface is important. So land conditions, soil moisture, and so on become important for the prediction. But as we move out beyond 30 days to seasonal and then longer timescales, then the state of the ocean is very important. So the ocean, as you all know, stores energy, for example, in the form of heat, which it then can release back to the atmosphere. So this heat can be transported around, it can be released sometime later and in different locations. So there's a predictability that comes from this aspect. So just to give you a little bit of a timeline of where we are with seasonal to decadal prediction, and this is my perspective on this. So in 1987, there was the first ENSO prediction by Mark Kane and Steve Zibiak. So this was a revolution, I think, in the idea of making climate prediction. And they put, they combined basically key understanding of the climate system into a very novel modelling technique, and were able to make ENSO predictions. So this was, I think, a first major step forward in actually climate prediction. So then in the late 1990s, there was quasi-operational seasonal forecasts. So the models changed and became more advanced. And then early in 2000, there was a lot of discussion about multi-model ensembles, and there was a realization that you need to combine different models to basically lead to more reliable predictions, more robust results. And a key in this was the Demeter project, I would argue. Demeter was led by Tim Palmer from the ECMWF. And actually, one reason for me to put this line in here was this was my first occasion to visit Taiwan. So in 2003, I think, there was a meeting arranged by Cheng Ta-Chen on climate prediction, and he had invited Tim Palmer, and unfortunately Tim Palmer couldn't come, but fortunately for me, I was able to attend. So this was a really nice introduction to me. So in 2007, then there was development of decadal predictions. So this is timescales from 1 to 10 years, and there was a few studies that showed that it was possible actually to predict on these timescales, and I will talk a little bit more about that in the next few slides. And then in 2013, the World Meteorological Organization with WCRP and the World Weather Research Program founded a subseasonal to seasonal project. So there was a recognition, I think also driven by user needs, that this is a timescale of great importance. So there's now a lot of activities on S2S timescales. And then in 2019, so this activity from decadal prediction has become sort of quasi-operational. So now I will show a few things on this shortly too. So we have now, based on these activities, a wealth of data that has become available. We have the subseasonal project providing data on timescales from the weather timescale, so 2 weeks to say 6 weeks. Then we have the seasonal from 1 month to 12 months, and you can go, for example, to the climate change services in Europe and access these data. And then we have now more recently from the WMO these multi-annual to 10-year predictions or decadal predictions that are available. And as you may not be very familiar with this, I wanted to just show you what this quasi-decadal prediction system is. So it's a multi-model system. It's contributed by centres all around the world. So there's roughly 15 different models contributing to this. It's led by the UK Met Office here. I can't remember the acronym, but this is the UK Met Office here. And you can see, for example, in Bergen are one of the contributors. We provide predictions every November for the next 10 years that are collected by the lead centre, and they go into these WMO annual reports. And this has been happening since, so I think the first one came out in 2020, and so you have a series of reports that come out every year out with an outlook of how, this period of time, 1 to 10 years, what is happening in the climate system. So we can predict the future to some extent, and that's described in these reports. So you might be asking yourself, has this timeline that I showed you from 1987 till present, and we have this wealth of data, to what extent has this led to climate services? And I'm going to focus in Europe, because this workshop was on Europe. So what I'm going to talk about basically is where are we now in terms of this? What are the current challenges? What is the way forward? Addressing climate services predictions and physical mechanisms. So the workshop touched upon all of these things. So it was we've really tried to integrate. So I'm coming from the climate research, so climate dynamics perspective, but we recognize in Europe that there's a strong need to integrate with people actually providing climate services. So the workshop had quite a participation from people working in this sector. And so the paper that we are writing is actually strongly motivated from this direction, from the climate services. So predicting, I wanted to start off by giving you a little bit of background of the challenges we face in predicting climate and weather in our region. So this is I was listening to talks earlier in this week, and I can see that there's some similarities, at least in the challenges that you have in predicting weather and climate. Here, you have the Western Pacific subtropical high, where in the North Atlantic we have the North Atlantic Oscillation and so on. But I think maybe you can take some of this, think about these when I'm talking about that. But there's also some interesting opportunities in our region that I want to emphasize. So first, in our region, we have the North Atlantic Oscillation. So you're probably not all very familiar with this, but it's a fluctuation of sea level pressure between the Icelandic low and the Azores high. And when it's in a negative phase, then you have a very fluctuating jet stream, and it leads to wetter and warmer conditions in the south and drier and colder conditions in the north. And when you have the positive phase, actually we have warmer and wetter conditions. So in particular, this arrow is almost pointing directly at Bergen, so we have much more rain. We have, in general, a lot of rain in Bergen where I'm living, but when we're in this positive phase, it's much wetter. But at the same time, this is for winter time, the conditions in winter are warmer. And it's the opposite in the south. So this is interesting and important for us. It's the dominant mode of climate variability. It's a challenge in the sense that it's driven by a lot of chaotic variability. So it exhibits not only a lot of year-to-year variability, which is the sort of the chaotic side, but if you look at this time series of the NAO, you can also spot some interesting decadal variations. So for example, from the 1970s to the 1990s, so this is I think 1996, was an upward trend in the NAO. So there's quite strong decadal fluctuations that potentially are predictable, as I will show. So on the one hand, the chaotic nature of the mid-latitude atmosphere makes climate prediction challenging. And as I'm going to show, so one of the challenges in our case in the European sector is that prediction systems are underconfident. So this has been discussed as a so-called signal-to-noise issue. And it seems that although this chaotic nature that you see in this time series would suggest that this not very predictable, this time series, we find that there is quite a degree of predictability. but you need to find methods to extract it. So now we come a little bit to the an opportunity in our region, and this is where I came into the field in terms of climate dynamics. So in the North Atlantic region, there's a very interesting decadal variation. So I hinted at it on the previous slide, but in our region we have very pronounced decadal fluctuations, much more than I think in this region you have sort of ENSO influence and you have a lot of interannual variability. In our region, it's the decadal that stands out. And so the top is the time series of Atlantic SST, so average between the bottom and the top of this graph, with the trend removed. And so you can see periods of time in the mid part of the last century that it was warmer, then it's been colder, and so on. So this is roughly varying on a 70 to 80 year time scale during the instrumental record. And it goes along with a pattern like this. So it is a bit stronger warming here in the subpolar gyre of the North Atlantic than in the south, but you have this basin-wide warming with a 70 to 80 year time scale. And it's driven, we believe, by changes in the poleward heat transport in the ocean, which is connected with this deep overturning circulation known as the Atlantic meridional overturning circulation. So when it's in a stronger phase, you get more transport of oceanic heat to the north and it warms this region. So this is a potentially predictable based on ocean dynamics. On the other hand, there's been quite a few recent studies that suggest external forcing is important for driving the predictability in this region. And this comes to what I'd said before about, on this timescales, initial value and boundary value problems or external forcing are important. So external forcing is potentially important, so changes in greenhouse gases and aerosols. And this is one of the challenges in our region, basically, and I would say globally, understanding the relative importance of these two factors, external forcing versus internal variability. So we have a very short record here. So, just for understanding this decadal variation. So the argument for the external forcing is that, it's been warming over the whole of the century, and then aerosols in our region, there was a reduction in aerosol emissions, and this led to this cooling part. So it's quite difficult to separate these two effects with such a short record. So from the climate service perspective, climate extremes come into the forefront. And this is, in Europe, we suffer these days a lot from heat waves. Right? And this is an example of the 2020-22 heat wave. And it claimed has a very devastating effect on our society in terms of this one, there was estimated 60,000 lives were claimed by this heat wave. At the same time, we have this particular event. So we often have cumulative or compounding events. So heat waves often go along with droughts, and this one was the most severe drought since 1981. So this type of variability is potentially predictable on sub-seasonal timescales based on large-scale drivers, teleconnections from the tropics. Near-term predictability changes, so this sort of decadal fluctuations, we can't predict the events, but we can predict changes in statistics. So we may be able to predict that there will be a few more heat waves or a few less heat waves connected with these multi-decadal changes we talked about on the previous slide. So that's a little bit of a background on the region of the North Atlantic. So what is the current status of climate services in our region? And so this is a descriptive summary of what came out of this meeting from a perspective of Europe. So in Europe, climate services have been primarily targeted this longer timescale adaptation. So in this meeting, we were interested in these shorter timescales, and there's been less attention paid to this near term, so sub-seasonal to decadal. But as here, it's demanded actually by users. There are a few examples of climate services developed for these shorter timescales, and I'm just going to present some examples for this decadal. But they extend from agriculture, fisheries, energy, and water management. And so the first example I will present here is for water management. So this is a study from Irini Tsatsili. It's a paper led by an Italian group. And it's looking at water resources management in a water catchment called Ebro in Italy. And these are based on decadal predictions. So you can see here, these are predicted changes. The the black on this side is the observed precipitation rate. The red is from the model predictions. So this is a 10-year prediction. And you can see here that it captures these decadal fluctuations. And on the left side, you see some, I'm not going to go into details, you see some results from the forecast system. And here, I just want to emphasize this part here, statistical versus dynamical. So these are anomaly correlation scores for this water management example. And you can see this statistical have quite high skill. Now, the statistical is actually a hybrid system. It combines predictability of the large-scale drivers like the NAO, and then translate this information with some empirical relations down to this water catchment level. So if you just compare the values on the left side here, so this sort of predictability that you see here can be transferred to quite high skill here. If you just take the raw data, it seems to be not very skillful. So this is one thing that we also need to consider, is how to translate information from global climate models to regional scales. But there are definitely interesting things that can be done here, but it requires quite a lot of knowledge and quite a lot of research at a very local scale. So the other example, one that I was involved in myself, is about fisheries predictions. So I was interested in the previous talk that there are fish stock that move. So this is work from Mark Payne in a study on decadal prediction of mackerel, and there was a few other species discussed in this paper, in the Icelandic region, or the North Atlantic Icelandic region. And so this is mackerel habitat plotted here from observations, and we can take the decadal predictions and use in this case, temperature data, and see, are we able to predict how habitat will change? And so, if you were a resource manager in the 1990s, you might want to know how will mackerel change in the future. So you could have used one of these decadal predictions if they were available then. And you would, with the model that developed here by Mark Payne, this habitat model, you would be able to see that, okay, the predictions would suggest an increase in mackerel habitat. And actually, that's the red line here on the shading. And so in this case, when we had the data, we could see that it actually verified. So then you could ask a question a bit later. So this is around Greenland. Can we expect mackerel to remain, right? And then we make a prediction here in 2010, and you see the prediction also levels off. So basically it shows that the system is able to capture these changes in mackerel habitat. So this ecological forecast can support decision making in a changing climate. So now, what about the current status in climate services in Europe? So user involvement in climate services design is, so these, I think a lot of these are probably very familiar to you, but I'm just going to go through them. So, and these are not just very specific to Europe. So one of these, user involvement in climate service design is critical to ensure climate services provide actionable information for decision making. So it's a recognition that you need to work together to provide a useful service. You can't just start by assuming what the service should be. Involving users in production can highlight key areas for service development. User engagement can take varied formats from wide scales. So this is different ways to do it. Surveys, workshops, direct discussion. You have to acknowledge that this is a very time-consuming aspect. A user-centered approach is important because it enables bespoke, so very tailored climate services to particular decision-making contexts. But it requires this co-production. It also requires capacity ability and co-development. So you have to work together to develop the capacity. This higher user participation comes with a risk of user fatigue. So you need to consider quite carefully when to involve users and how to involve them in this process and how often. But it's critical to involve them, but you also don't want to have get this user fatigue. So in terms of challenges, we identified 4 challenges in developing climate services. The first goes to implementation and reach. So this is how to expand the climate services. So going from research-based subseasonal to decadal case studies. So prototypes of seamless climate services to providing repeatable or transferable services to users or sectors is a big challenge known as upscaling. So how this small, like I showed you earlier, these are basically pilot studies like this this water resource management in Ebro. How do we translate this to a larger scales into other sectors? The challenge lies in extending cross-sectorially, while services to be adaptable to include to local information about hazards, exposures, or vulnerability. So how do we go across sectors? Another challenge is governance. So climate services providers advocate strongly for a governance framework to proactively generate best practices, ensure good standards across public sector and industry providers, and provide accreditation to guide users to choosing service providers who demonstrate best practices. So in Europe, we are seeing, many people coming up, many, industries or small businesses coming that are offering to provide climate services. And so, if you're just thinking about cost, and you just want to buy a climate service, you might just go for the cheapest one. But this may not be, the best one. And so this is about this. So how to ensure that there's good standards. So for standards to be impactful, methodologies of products should be transparent and tied to regulation. And one of the challenges here is around which actors should shape the discussions on standards and regulatory requirements, and what value and knowledge systems characterize for these sectors. So you might think, this is one of the examples, the private sector may not be able to provide equitable or reliable climate services for the finance sector. This is because the finance sector uses a lot of proprietary methods, right? So they're sort of secret information. So how this would be quite a challenge in this case to develop governance, involving them in governance. I just wanted to highlight one of the activities in Europe. So I'm not involved in this at all, but it's related to governance. So there's a European network on developing standards to increase uptake. So once you can convince people or build an understanding of how good the products are and what is possible, then it's possible to increase the uptake of the products. And so Climate Europe 2 is aiming to do this. It aims to develop future equitable and quality assured climate services of great value to society, which will provide trustworthy, so this is quite an important word here, trustworthy, user relevant and usable information. So to get uptake, we really have to build trust. And so this project or network deals with standardization, supporting it with the aim of increasing uptake. So maybe you will find this website interesting to you. The third challenge here is communication. So co-production requires multi-directional information flow between producers of climate prediction information and users, including both climate service producers and those that use the information for decision making. So this goes back to the co-production. So to manage to co-produce climate services, you need to have good communication. Timely and purposeful communication is important at each stage to transform climate information into human stories and nurture engagement and mutual understanding, especially around complex issues for climate prediction, such as understanding skill and risk. So, in our community, we often talk about probabilistic forecasts, but how do we translate that into information that decision makers can use? That's one of the challenges here. And so communication is a time-consuming process. So it's often under-resourced by parties, so ensuring this flow of information is effective and efficient remains a major challenge for climate science and services. So, although we may hope and recognise the need for communication to develop good, to co-produce good climate services, we have to then make sure that the resources are there to do it and that the people interested in doing this are properly funded. The last, which relates a bit more to the technical side and what I work on, is technical and logistical issues. The usefulness of climate prediction information for climate services is currently constrained by a range of technical challenges spanning data accessibility, timeliness of open access availability, and compute resources needed to post-process data. So there's a lot of development in this field in Europe to address this one. And, this long list of available data sources, mostly hosted at European centres, is mitigating this issue. In addition, seasonal to decadal prediction data available at coarse resolution. So this goes, and the previous speaker also talked about the need for higher resolution. So compared to downscaled regional climate predictions will provide this higher resolution, there's a limited forecast quality for commonly desired variables such as precipitation, surface wind speed, especially for extremes, which users are highly desire. So, we have data coming online, but it's still relatively coarse, and the skill of this data is also questionable. So this makes the uptake of development of climate services a challenge. The use of robust information for decision making relies on skillful forecasts. Therefore, development of useful prediction information from seasonal and decadal predictions into climate services is still relatively rare for this region. So this is a challenge for us, how to improve our skill or extract skill from what is available. So the status of climate prediction and challenges. So for the sub-seasonal forecasts, we have this type of graph about the different sources of predictability from days to centuries. So in this sort of sub-seasonal, we have atmospheric processes like Rossby waves, we have soil moisture being important, we have remote forcing. So some of these are definitely things that we can predict on these timescales and lead to predictability, as you will see on this graph. So this is the 2021 heat wave, and this is the target period in Europe. This is the target here. You can see a large warming of 4-6 degrees. These are forecasts from the 10th of June from the ECMWF system. So you can see already a couple of weeks before that there's already hints that a heat wave is coming. So you can use this type of information to increase your preparedness. In general, for prediction of heat waves, the thermodynamic aspects are easier to predict, and we have skill on this. Dynamic aspects that you see on this type of graph, it's much more challenging. And these are you could argue, the more important ones. So this skill on seasonal timescales in our region too, and this is the North Atlantic Oscillation Index that I showed you earlier in black, and just a shorter period from 93 till 2012. And the yellow line here is predictions from the ECMWF system, from the UK Met Office system, started in November and predicting the winter time, December, January, February. So you can see actually there seems to be quite a lot of agreement between these two time series. What you don't see immediately is what we refer to as this underconfident. So you can see these dots are the individual forecasts, and there's a very large spread. So it seems that you may not trust actually the ensemble mean of this given this large uncertainty. But the correlation with the observations is around 0.6 of the ensemble mean with this thick line here or this thick line here. But if you were just to consider the spread here, you would have expected a correlation of around 0.25. So this is what is referred to as the signal to noise issue. And our system seemed to be underconfident. So one of the reasons for this is, the mechanisms and their representation in the modelling systems and our understanding of them. So we have here, for an example here, the predictability of the NEO is mostly derived from the tropics. You have here teleconnection pattern in early winter, which involves the Indian Ocean and ENSO. So this is November, December, and you have these two pathways which lead to there's a competing effect in the tropics that leads to this low-high anomaly here. If you later in the winter, where ENSO is important, so the Indian Ocean signal has decayed, you just get one sign, and then you get the high and the low. So there's these competing effects, and the models have to reproduce this. There are other challenges related to these teleconnections can vary in time. So they can be sometimes more strong than others. If there's a physical mechanism behind this, we might identify windows of opportunity. And there's studies looking at this, and so we could, based on our physical understanding, we could say when we expect predictability and when we don't. So that's very useful. One of the challenges in our region is that, the local forcing, so like Atlantic SSTs or Arctic sea ice changes, their impact on the atmosphere is not very well understood, actually. And so the local sources of predictability are not that clear. Now, just for the decadal timescales, we have here, for the 2021 heat wave, 2022 heat wave, 2023 heat wave, 2024 heat wave, 2025 heat wave, 2026 heat wave, 2027 heat wave, 2028 heat wave, 2029 heat wave, 2030 heat wave, 2031 heat wave, 2032 heat wave, 2033 heat wave, 2034 heat wave, 2035 heat wave, 2036 heat wave, 2037 heat wave, 2038 heat wave, 2039 heat wave, 2040 heat wave, 2041 heat wave, 2042 heat wave, 2043 heat wave, 2044 heat wave, 2045 heat wave, 2046 heat wave, 2047 heat wave, 2048 heat wave, 2049 heat wave, 2050 heat wave, 2051 heat wave, 2052 heat wave, 2053 heat wave, 2054 heat wave, 2055 heat wave, 2056 heat wave, 2057 heat wave, 2058 heat wave, 2059 heat wave, 2060 heat wave, 2061 This is an example from the Norwegian climate prediction system, but actually it's, if you look at any of the papers on decadal prediction at the moment, you'll have basically the same picture. So this is the skill in predicting sea surface temperatures at 6 to 9 years ahead. It's from a reforecasting period from 1960 to 2010. There's a forecast done every year during this period with an ensemble size of 10 members. And we are simulating ocean data. So this is the correlation with SST. And you see high correlations across the whole globe. So maybe you're surprised, maybe you're not. So I think if you were to think about it, you probably wouldn't be that surprised because the world has been warming, right? And so most of this skill actually is coming from global warming. Some of the, the patterns are not, but the overall warming you could expect due to global pattern would be related to external forcing. So this is, the graph on the right is actually the added skill from doing the data assimilation, from doing the initialization of the ocean. So it's the difference between, the historical simulations versus our initialized simulations. And so you see actually only in the region of the North Atlantic, where at the moment is where initialization really adds value. So that's one of the opportunities for us. So this is the ocean heat content, and the overturning circulation that I mentioned earlier is important. But the big challenges I referred to earlier is what is the relative importance of external forcing versus internal variability? This is one of the open questions in our field of decadal prediction. So this is the corresponding figure for precipitation. And you see this is the total skill of the system. This is the skill related to the ocean only, or the initialization of the ocean. And so you can see that these are now looking more similar. So the skill in precipitation skill is coming largely from dynamics, but it's very patchy. And you can see it even looks negative here, which switches from positive. I just want to highlight again, coming back to this signal to noise issue, and that actually there is quite a lot of skill. So the left, since my time is running out, I'm not going to explain in a great detail here. The left side is the raw forecasts. So the black is the observed rainfall in Northern Europe. And the red line is the raw forecasts. And on the right side here, you see what is sort of a corrected forecast system. So you can see here, when we do some filtering of the data, identify ensemble members that most closely match the ensemble mean here in phase, we get this one, and then we get a correlation of around 0.7. So there's actually a lot of skill there, and you could predict the decadal changes in rainfall in the Scandinavian region 10 years in advance. So if you have questions, we can talk about this later. So what are the ways forward? One of the biggest challenges, and I would say the biggest challenge in our field of climate prediction, and I would argue also in the field of climate change projections, is model biases. It's one of the hardest things to tackle. So here you see errors in sea surface temperature in our climate models. And this is, I think, from CMIP 6, but probably CMIP 5 based on this one. But these errors don't change very much between model generations. And the errors in the North Atlantic, for example, are very large, and they lead to a degradation in skill, which is shown on this figure, which you can just see the drift here. This is drift in our North Atlantic predictions. I'm not given time, I won't talk about that. So I'd like to talk a little bit about how we would address these issues. So there's two aspects to consider related to models. The importance of climate service resolution, as we heard, is very important, but also ensemble size. So these two things are sort of competing with each other and deciding what type of system we would produce. And these need to both to be considered. So increasing model resolution does show some promising results, particularly in the representation of processes, like interactions between land surface and atmosphere, or diurnal cycle, and things like this. But it's not a panacea, so it's not a full solution. There's still a lot of issues, and we see in our first generation of these storm resolving models very similar biases. So on the one hand, it's not a solution on its own. So I would say it's not a solution in the short term. And the more challenging thing is that these are very expensive, and model improvements take a long time. So it's going to be a long time before these high resolution models are really usable, I would argue. So dynamical downscaling is another approach, but it has its own issues. but we do need alternatives. So there's a lot of interest in our community to understand how these, all these new AI approaches that are showing a great promise, how to combine them, how to use them on their own, how to combine them with dynamical systems. Can we use supermodels, which is another approach for combining models? I think I'll just go to this slide. So this, in terms of climate services, there's also how we will address these challenges. So technically, we want to improve the capacity to produce seamless timescales. This requires investment in expertise and infrastructure. We need to develop better methods for decision making, to transfer information from probabilistic information with large uncertainties to be able to make decisions properly, and we need to assess the value of these. The implementation and reach, there's continuing engagement between researchers and users to maximize usefulness of the services, and this requires sufficient resources for all parties. So this goes back to having enough time to communicate and interact with each other and have the resources there. So AI approaches, so these large language models, for example, can be one way to solve some of these things from engagement and the upscaling. Maybe there are ways, but there's a lot of caution that is needed here. We are ready to trust these large language models and how they interpret our graphs and how they provide advice. So the last point here, maybe proactive engagement of existing sectors, networks is needed to avoid recreating multiple spaces of information exchange. So, if each individual goes out and tries to develop a climate service, then there's going to be a lot of overlap and duplication. So we should make more use of networks. I think I'll just finish here given the time. So this is what I tried to shortly summarize. So climate services in Europe for subseasonal to decadal timescales have been slow in developing. This has been related to a number of issues related to, partly the technical challenges, availability of data, the quality of the data is one of the major issues in our region. So the skill has been low in the past. I've tried to argue that there is quite a lot of skill. You just need to know how to extract it. So the situation is changing. There are new approaches to be able to extract this skill and to be able to deliver the required information. But model biases, in my view, are the biggest challenge to enhancing prediction skill, and alternative methods are required to deliver this information in a timely fashion. And we have now, with these hybrid AI approaches, quite a lot of promising things developing. So thank you very much.
Thank you, Dr. Noel, for his excellent talk. And it is very interesting that, as we discussed previous day, that in Norway, he developed the model from the decadal, and right now they would like to more focus on the subseasonal to seasonal scale. But however, here in Central Valley Administration, we developed the subseasonal to seasonal model systems, and now we try to move forward to the decadal prediction. So I think that's the common sense that the subseasonal to decadal is definitely very important and critical for the climate services.